Okay, good morning, Year 12. We're going to be looking at mathematical induction, and we're going to look at this question here. Okay, so we've got to prove by mathematical induction that the left-hand side equals the right-hand side, where k is an element of the natural numbers. Now, we've done sigma notation before, so I'm not going to go through that with you. I'm just going to get straight into the question. So, first of all, we want to let n equal to 1. Okay, so therefore, the left-hand side is equal to, I'm just going to keep it in sigma notation for this video, and then I'm going to do another one where I expand it and get rid of the sigma notation. So that way you can be reminded of both ways of doing it. So all right, so just subbing in k equals 1 there, you're going to get 1 over 3 times 1, and that's equal to a third. And then we have right-hand side. Right-hand side will be 1 over 2 times 1 plus 1, which is the third, which is obviously equal to the left-hand side. So therefore, true for n equals 1. Now, we're going to assume true for some arbitrary integer. We'll say n equals k. So k, you could use n equals p or some other letter. I'm just going to use k. Therefore, suppose I guess technically we could use a different letter to k. I guess we could use p. So suppose that we go from k equals 1 to p, where p is a positive integer, and 2k plus 1, 2k minus 1 is equal to p over 2p plus 1. Okay, so that's our supposition. That's our assumption. Oops, just missed out there. So we're going to suppose it's true for n equals p. Okay, now, next. We've got to then prove true for n equals k plus 1. So prove true for n equals k plus 1 or p plus 1, it doesn't really matter. Okay, so that means, and I'm going to keep the sigma notation again, we've got to prove that sigma k equals 1 to p, 1 over 2k plus 1 outside of 2k minus 1 in brackets plus 1 over, it'll be 2 brackets p plus 1 plus 1 in brackets again, and then 2 brackets p plus 1 minus 1 is equal to p plus 1 over 2 outside of p plus 1 plus 1. Okay, now we can tidy that up a little bit. So we've got to prove that sigma k equals 1 to p 1 over 2 k plus 1 2k minus 1, put that in brackets, plus 1 over, now this will be 2p plus 3, and then 2p plus 1, okay, equal to p plus 1 over 2p plus 3. So that's what we've got to prove, and we're going to start off with the left-hand side here. Okay, so let's just turn the page. Okay, so we've got to prove, so we'll start with the left-hand side. So left-hand side is equal to sigma k equals 1 to p, and then we have 1 over 2p plus 1, 2p minus 1, plus 1 over 2p plus 3, 2p plus 1. Okay, now from our assumption, okay, so this part here, which is the reason I put it in brackets, that we can use our assumption on this. So that will be equal to p over 2p plus 1 plus 1 over 2p plus 3, 2p plus 1. Okay, now we want to put this all over one denominator. So I've got to make the denominators the same. So the only thing I've got to do really here is put a 2p plus 3 there, and then do the same thing for this. Okay, so now I can put everything over one denominator. So I've got 2p plus 3 and 2p plus 1. Okay, then on the numerator I've got this plus 1. Okay, so the next step is to expand the brackets. So I'm going to get 2p squared plus 3p plus 1 over 2p plus 3 outside of 2p plus 1. Okay, now I can factorize the numerator, so 2p and p, 1 and 1, and then it'll be 2p plus 3, 2p plus 1. Okay, so I can cancel that with that, common factors. So I end up with p plus 1 over 2p plus 3. Which equals the right-hand side. So prove that the left-hand side is equal to the right-hand side. So, therefore, true for n equals p plus 1 if true for n equals p, since true for n equals 1, the formula is true for all positive integers. Okay, so that's the end of our proof. Now, I'm going to post another video of this, but with the sigma notation expanded, but that's enough for you to do 503, question 1 to 6 from the textbook.